بسم الله الرحمن الرحيم. سلام الله عليكم شباب. What type of failure do we expect in compression members? Two types. Local buckling. Speaking now English. What types of failure do we expect in compression members? Fracture, crushing, or buckling. So we have short members and short columns, and we have what? Long columns. But in steel, we can consider all columns to be what? Long. It's very rare that we find a short column. Now, buckling is the main item in design of compression members in steel. There are two types of buckling. One, overall buckling, and the other, local buckling. Concerning overall buckling, we derived two equations. One in the elastic range, where F critical equal 0.877 B Euler, and B Euler is pi squared EI over L squared, or B Euler equal pi squared EA divided by KL over R all square. And we have another equation for inelastic buckling. Now, concerning elastic or inelastic, it is common sense to draw the curve like this. This is F critical. F critical. This is F critical. And this is KL over R. It is common sense to say that at F yield, when the member reaches F yield, it's no more elastic. We go into an elastic range, and the curve will be like this. However, this is F yield now, and the curve starts from here going into an elastic range. Why? I told you that in the final, at least, we will ask questions about concepts. So every concept we explain throughout the class, you will be asked about in the final. What are the reasons behind going to an elastic range before we reach a field? What about residual stresses? We said that the member have what? Has residual stresses. The member has residual stresses that can reach how much? To what value? You go to your exam next Saturday. What is MR? MR, how do we calculate MR? 0.7. Why 0.7? Because we have 0.3 F yield, what? Residual. So the 0.3 F yield residual is one factor. The out of straightness, we never have a column that is what? Straight. We have what? Out of straightness. This does not affect bending capacity, but it affects when we have an axial load that will introduce an additional B delta effect. So we spoke about other items that affect this curve. And remember that this curve should differ from shape to shape. However, AISC adopted one shape where this equals to F critical equal 0.658 0.658 to the power F yield over F Euler multiplied by F yield. Now, this curve is being done where the abscissa is KL over R. What is L? Length of the member or height of the column. What is R? What is K? Effective length factor. Let us remember some types of effective length factor. What is K for this? 2. For this, 1. 0.7 theoretical and 0.8 what? Practical. What about frames? How do you find K factor in frames? Yes, we find psi A, which is summation of EI over L columns divided by summation of EI over L beams. And we find the psi B. And we have 2 nomograms, one for brazed and the other for what? Unbrazed. For brazed, what is the value of K? What are the limits of K? It is between what and what? Between 1 and 0.5, not 0. Between 0.5 and what? And 1. That's why for brazed structures, it is immaterial whether you take K1 conservatively or you calculate it exactly. However, for unbrazed, K is greater or equal to 1 and less than. Here it is very important to calculate K, and we said before that if K is more than 2, 2.3, 2.5, be careful to look again at your structure. I don't recommend using structures with very little stiffness of beams. The more the stiffness of the beam is, the better the structure you will have. The language might appear a little strange for you at present, but I feel if all teachers commit themselves to speak in English, you will only suffer maximum 1 week. And afterwards, your hearing in English will be what? Much better. If you start asking questions in English, with time it is very easy for you to speak in English. If you feel not confident in talking in English or speaking in English, it is for one reason, that you think in Arabic and try to translate your thought from Arabic to English. This is the worst way to speak in any language. If you want to speak in any language, think in the terms of the language. Just express your thought while thinking in English. You will find no trouble. But if you start thinking in Arabic and trying to translate that words in English, you will never succeed in making any conservation. If we do not teach you how to speak in English, I don't know where you are going to learn this. Especially we hear that some English classes, English 101 and English 102, are taught by some in Arabic. Is that true? All of it is in English. No word in Arabic in the class? Yes? Different? Well, start talking in English inside the class, because once you graduate, you are forced in many companies to write in English, to speak in English, so make it familiar for you. Now, the third thing that we want to speak about is local buckling. In local buckling, we said, since the maximum stress that we approach in compression members is a field, local buckling, if we took a plate, subject this plate to compression, then the stress strain diagram will be something like this. The asymptote will be a field. The member which can deal such this with deformation is called compact. True. The member that reach a field and then goes down is called non-compact. And finally, any member that does not reach a field is called cylinder. In columns, we need either compact or what? Or non-compact. And for non-compact limitations, we took that B divided by TF should be less or equal to 0.56 square root of E divided by F yield, and lambda and H over TW less or equal to 1.49 square root of E divided by F yield. This is for unstiffened. Unstiffened plates means that plates that are connected only at one part, like the flange, where this is B and this is TF. And this equations for stiffened plate, like the web, where this is H and this is TW. Of course, when we took an angle, is the angle stiffened or unstiffened? Unstiffened, so we apply that law to it. Any questions about compression, members?
That equation, B is divided by 2TF, not by TF.
Now listen, if I am thinking of B to be this total, then you are right. But if I am thinking of this to be this only B, then this is the equation. So make sure that, what do you mean by B? If you mean B the total flange width, then you are right. If you mean by B what I wrote on the blackboard, then I am right. And both are speaking about only one item, because you know that this is almost 1/2 what the total B. I promised you that I will give you a truss, and I will design the truss according to SAB. And here at the end, if you do not verify the calculations inside SAB, then I am going now to prove to you that all of you will produce an unsafe structure. Let us take the example that I want to talk about. This is a 3-hinged arch where we want to carry 75 kilonewton. The span lengths are 9 meter, 9 meter, and here we got 4.3 meter. The load is very small. We are talking about 7.5 ton, and we want to import the sections from Europe, and we want to use I section. In Europe, it's called IBE sections. So let us try now to design such a truss. Make sure that it is written in your notes, because we are going now to shut down the light. Thank you very much. The units are kilonewton meter. File, new model. Let us take grid only. We have in X direction 3 grid lines. In Y direction, there is no Y direction. In Z direction, we have 2 grid lines. What is the spacing in X? The spacing in X, 9 meter. And the spacing in Z, 4.3. Let us do XZ plane and draw the members of the truss. Now, to draw the diagonal member, we only have to just divide these into two, added lines, divide the frames. We divide them into two. To show the intersection of the lines, we just make the points visible instead of invisible. Now, the remaining lines are the ones that connect this to this and this to this. Now, suppose I chooses all of these to be fixed, and I set releases at the joints. Do you think that the analysis will change, will be or will be the same? The same. So don't worry if you put them fixed, as long as you release what? The members. So if we say now assign, joint, restraints, whether you put fixed or bin, it doesn't matter. Now we want to choose these members to be IBE. So let us first of all select them all. Assign, frame sections. Let us import. And we said that we are going to import I sections from Euro. So here's Euro, Pro, open. Now you can take all IBE sections, but from my experience, IBE, because the load is small, will not exceed the 240. But let me get it far to 270. Okay. Here is okay. And here add new property. We want an auto select list of all IBE selected. Let us now assign the load. Assign joint loads, forces, minus 75. This is the ultimate load given. And here we have define load patterns. We want we do not want the dead load to be involved for this question. And the load combinations we need is only the dead load, because it is an ultimate load. It is just the dead load what acted. We can do the analysis. No need for model. And we can save our results on C. This is the truss. Now, in order to design, we select all. We start by design, steel frame, view revise preferences, and we can select the code we are familiar with. And also design, steel frame design. We can select the design combinations to be not automatically, or just to be the combination that we defined. We can start our design. Now, after finishing our design, we want to see if we can see that we have 8 frames left, are different. I don't want to go back and forth. I just wanted to select IBE 200. Notice that you got IBE 160, 270O, 220O. I will show you that 200 will be sufficient. Assign, frame section, IBE 200. Okay. And here, if we analyze it, and then design it, you find that none of the members are what? Are in the red zone. IBE is just approximately, you got 0.983, so it is less than 1. SAB, if it is more than 0.95, will give us section is what? Overstressed. Now, it is an IBE 200. You did design it. You don't want to do verification, or you wanted to do just 2 types of verification. Can any one of you draw this section at the blackboard. Show us how he's going to send this to the manufacturer. And I will prove to you that if you just rely on SAB, this structure will collapse. Here's the eraser. Let me draw the section for you. Let me draw the section. This, all of it, IBE what? 200. So I will do it like this. Let me have space. I will do it like this. Of course, not to scale, but to give you an idea. The last member that will, of course, this will long until we get the member that comes from here. And welded here. Of course, the members are connected at the joint because this should be in the middle. If I make the vertical, it will not reach the way it should. So, if I want to draw it more correctly, it will be something like this. See. And finally, of course, what is wrong of doing the truss like this? Isn't it IBE 200? I claim that this truss will collapse. Can any student tell me why?
No bracing in the middle.
Okay. And SAB assumes what? Bracing in the middle. Now, I want to do verification of this. Now, what does it mean that I don't have bracing in the middle? This is a 3-hinged arc that cannot be braced in the middle. It's just an arc made to carry the loading. According to SAB, he assumed L to be between this point and this point. This is what SAB assumes. Now, unfortunately, if this member is going to buckle this way, then the whole length will be what? Valid. Let us see what will happen. If I say KL over R, now you got this equal 4.3. This is equal to 9. If you do some arithmetic, you will find that this member is 5 meters. And the other member is what? It's 5 meters. Now, let us differentiate between someone who truly understands steel and someone who doesn't understand steel, he just put them, take IBE 200, make the shop drawing, send it to the fabricator, do such design, and the structure collapse. Let us see why. Now, concerning it is been, then K equal 1, but now, instead of L being 5 meter, now L is what? 10 meter. Because if it's going to buckle this way, it will buckle about which? Major axis or minor axis? Minor axis. So we have 1 by 10 over R, where R, we can get it from the program to be 0.0223. Let me show it to you. This is IBE 200. Modify show. Section properties. If you look at RY, it is 0.0223. Remember, Rx how much? 0.0826. We will come to it now. So 0.0826. 0.0826. Now, if you put KL over R1 by 10 over this, we will get 448. Once we get 448, we can get phi F critical. Phi F critical will be 8.6. Of course, you will not find it in the table. So you have to find F critical to be 0.877 B Euler. And if you apply the equation, it will be 0.877 multiplied by pi squared multiplied by E, which is 200 by 10 to the power 3, divided by KL over R, which is 448. This will give you 8.6. Now, if you want to calculate phi B critical, what is phi for compression member? Compression members. 0.9 multiplied by F critical, which is 8.6, multiplied by the area, which we can get it from a member to be 2.85 into 10 to the power 3, divided by 10 to the power 3. This will give you 22 kilonewton capacity. 22 kilonewton capacity. Just remember that the area is what? 2.85. Let us make sure of that. This is the area. It is 2.85 into 10 to minus 3 meters squared, which means 2.85 into 10 to the power 3 millimeters squared. Now, what about the force in the member? If we look at the forces in the member, you will find that the force in the member is what? It is not apparent. Okay. Look at it. 85 kilonewton. Its capacity is 22 kilonewton, and the ultimate load is 85 kilonewton. This will lead to collapse. That's why in your exam, we gave you two members, one compression, one tension. We gave you a load, either gravity or wind loading, and ask you to design it using SAP, to verify it by hand calculations. Now, if you design it using SAP and you didn't verify your calculations by hand calculations, a collapse can occur. Personal computers started in the early 80s. Since then, failures in engineering structures are in increasing percentages. The reason is that we have many engineers who find it quite easy to rely on computer without verifying its output. Now, people who are classical knew the importance of verification. I remember a friend of mine who was doing some research for NASA, and he was developing some sort of arm that will make the helicopter make a turnover, and that arm, he did analysis of it using finite element. NASA asked him to do classical solution. The shape of the arm was something like this. Now, he was unable to do classical solutions, so the one who helped him to do that subdivided the deformations into axial, shear, moment, and torque. And it turns to be that the torsional deformations are hundreds times more than the others. So he was advised, in order to decrease torsional deformation, to make this section what? Closed. After doing the classical solution, and the classical solution brought the same answer as the finite element solution, NASA approved his research proposal. Now I want to tell you how we can design the member without doing any change, how we can do the design and the design be safe. All what we need to do is to put this member like this. Which means, instead of the I section being like that, what do? We turn it like this. Now, we are making the long member, if it's going to buckle in the long member direction, it will buckle along the strong axis. So KL over R will be 1 multiplied by 10 divided by 0.086. So KL over R will be 1 by 10 divided by 0.086, and this will be 121. We compare it with KL over R in the weak direction, which is 1 multiplied by 5 by 0.0223, because now it's braced at the middle in the weak direction, and we find that KL over R equal here 224. By this, we can find F critical to be 4.3. And phi B critical to be 88 kilonewton. Of course, this is governed because this is much larger than what? 121. But here, an 88 kilonewton, the member is safe. What was the force in the member? 85, so the member is safe. I know so far that many students don't take our speech in verification of SAB to be on the things that stay in their mind. They think they will do it just for me, and once they graduate, they will not do it anymore. So many students are so much in interest to learn SAB, feeling that SAB will provide them with a successful career. What provides you with a successful career is your thoughts, not SAB, not any other means. The university here just teaches you how to think. If your thinking is improved each quarter, then I can assure you that you got the tools to be successful once you graduate. If your thinking does not improve quarterly, I don't want to say on a daily basis, it should be on a daily basis, But if it doesn't improve quarterly, I don't think any one of you will pursue a successful career. All what you can do is just make copy designs that are available, and you just copy them. And if a failure occurs, then you start asking someone who used to develop his thinking ability in order to solve your problem. Next Tuesday, I will review it with you, the beams and the beam columns. And I hope by this we will review the whole material and get you prepared for what? For the final. Any questions? Potential for sure not. But if you think about beam column, for sure you need to calculate the capacity of the beam column in order to know which interaction equation to use. So compression members are with you. We cannot subdivide them, but we told you that you will not be asked about trusses or tension members. So concentrate on beams, beam columns, and connections. And of course, the material that we didn't ask so far anything about, which is beams and beam columns, will get the larger mark, and connections will get what is left for it in the marking process. Any questions? See you on Tuesday.